Hi students, in this video we're going to talk about motion in space. The problems that we solve are going to be in two dimensions when we get to the application kinds of questions. Our first example, we have to find the velocity, acceleration, and speed of an object. So we should know from Cal 1 that the derivative of position is velocity and the derivative of velocity is acceleration. And if we're talking about speed, speed is going to be the magnitude of our velocity. And if we were starting from acceleration, the antiderivative of acceleration is velocity. And given some initial value conditions, the velocity equation can be solved specifically for a certain time of t. And then if we take an antiderivative of velocity, we can get position. So we're going to do those two things in the second and third example. For the first one, it's pretty straightforward. So we have this position function, position vector, e to the negative 2t, t squared, and cosine t. And we want to find the velocity, acceleration, and the speed. So our velocity, so r prime of t, which is going to equal velocity, is going to be negative 2 e to the negative 2t, 2t, and negative sine t. So I guess immediately we can go ahead and find our speed. So we'll say speed is equal to the absolute value of velocity or the magnitude. So that's just going to be each component squared added together and under the square root. So we're going to get negative 2 e to the negative 2t squared plus 2t squared plus negative sine t squared. And most of the time this won't simplify to anything useful, so we're just actually squaring these components. So we would get 4e to the negative 4t plus 4t squared plus sine squared t. And there is no identity we can apply here that makes this simpler, so we just stop here. And so next is our acceleration vector. So the second derivative of position, which is the derivative of velocity, which we're going to call acceleration, is 4e to the negative 4t, 2 and negative cosine t. And so that's our velocity, speed, and acceleration. Very straightforward, just finding a second derivative or first derivative and its magnitude. Things like the chain rule, quotient rule, and product rule would apply if we had components that required those kinds of derivatives. So hold on. Next we have, so we're given this acceleration vector that's cosine t and 2 sine t, and we have an initial velocity of 0, 1, and an initial position of 1, 0, and we want to find the velocity and position vectors. So given acceleration, we know that velocity is equal to the antiderivative of our acceleration vector. And then we're going to say like, well, plus up to a constant, but we'll see that. So in this case, that's going to equal the antiderivative of so we have cosine t and 2 sine t dt. But we also have this initial velocity condition that we'll apply. So the antiderivative of cosine is sine t. We'll keep this in vector form. So sine t, and the antiderivative of 2 sine t is negative 2 cosine t. And both of those are up to some constant C1 and C2. So with this initial condition of the velocity being the 0, 1 vector, that means that V0 is going to be the sine of 0. And we're going to combine these. So sine of 0 plus C1 and negative 2 cosine of 0 radians plus C2, and we should get the 0, 1 vector when we do that. So sine of 0 is 0, so this is going to imply that C1 equals 0, and then negative 2 times cosine of 0 is negative 2 plus C2. So we also get negative 2 plus C2 is equal to 1, which is going to imply that C2 equals 3. So our specific velocity function here is velocity is, as a vector, sine t, and what's it, 3, we'll say negative 2. I keep my variables first. So negative 2 cosine t plus 3. And so now for position is going to be the antiderivative of our velocity vector, which is going to be the antiderivative of sine t, and the second component is negative 2 cosine t plus 3 dt. And when we do this, we're going to get a vector that is negative cosine t and negative 2 sine t plus 3t, and again up to some constant that we'll have to solve for. I think we're given so the initial position is 1, 0, so r of 0 is 1, 0, and so that means that when we substitute in 0 for t, we should get that 1, 0 vector. So that's going to be negative cosine 0 plus c1, plus c1, and negative 2 sine 0 plus 3 times 0 plus c2. And so again, if we take this first component and set it equal to the first component for our position vector, we get 1 is equal to, so negative cosine 0 is negative 1, so negative 1 plus c1 is going to imply that 2 is equal to c2. And then 0 is going to equal 0 plus c2, so it implies that c2 is 0. So our position vector is, where are we here? So, so negative cosine t plus 2 and negative 2 sine t plus 3t plus 0. So that is our specific position vector under those conditions. All right, so a lot of what we're going to do in class, in our group work or individual work, is dealing with motion in space. Now, I like deriving this stuff so I don't have to remember formulas, because you just integrate acceleration and velocity and you always get where you're going. And so when we're talking about two-dimensional motion, really what we're talking about is if an object, I can draw better, if an object is launched from the origin, it's going to, assuming it doesn't travel in like due east or due west or something horizontally, it's going to take a parabolic trajectory. And these formulas work based on starting from the origin. So assuming we launch something upwards, it's going to take a trajectory that is parabolic. And so we should just know from like algebra 2 that at the vertex of that parabola, that's going to be our maximum height. And we should know from calculus that the velocity is going to be 0 at the maximum height, which means that the y component of our velocity vector is going to be 0 at that point. So the maximum height is going to correspond to the y component of velocity being 0. And that's going to be some time t. And then to find the maximum height, then we just take that time value, substitute it back into our position function. This is analogous to us doing the relative maximum and relative minimum in Calculus 1. They just kind of dress it up and call it something different. And so these things like flight time, range of flight, and maximum height, those are things that, again, if you have a formula and you like to remember that, cool. But it's all is this V0 sine theta. This is really just a y value. So we can always derive this stuff if you forget. Again, I don't use formulas generally. I try to just derive everything as we're going along. So the important part here is that this is from the origin. And if it's not from the origin, we'll have to like use other things like deriving the formulas in general and starting out. So for these formulas, what's important is the velocity. The initial velocity is the speed vector times the angle of launch. So we'll say like V0 is equal to the speed times cosine theta and sine theta. So our initial velocity is going to be that if we have to actually find it. So we'll see that in a moment. So for this last example, and this is just problem 42 from page 851. It's hard to come up with my own kinds. So a rock is thrown from the edge of a vertical cliff 40 meters above the ground at an angle of 45 degrees above the horizontal. How convenient. With a speed of 10 square root 2 meters per second. And we are assuming the origin is the base of the cliff. So all of those formulas, they're not going to work. We have to derive our own. So for the first thing we need to do is find the velocity and position vectors. And so let's go. So let's see what we can get from this problem. We know that the initial velocity, so we'll say V0 is 10 square root 2 times the cosine of 45 degrees and the sine of 45 degrees, which is, all right, so that's square root 2 over 2 for both, right? So 10 square root 2 times the square root of 2 divided by 2 is 10 times 2 divided by 2, which is 10. So we get this vector 10, 10. If you need to pause to work that out, do so, but that's what we get. And so then our initial position, since we're starting 40 meters above the ground, our position vector's initial position is going to be 0, 40. And since we're using meters per second, we're going to assume that G is equal to 9.8. But what we're assuming also is that gravity is the only force acting on our object, no wind resistance and stuff like that. So if we have to find the velocity and position vectors, there are two ways to think about this. You could, again, just use these formulas, but they require that you remember the formula. They're not that hard to keep track of, but like say you forget, and so we'll work under the assumption that you forget the formulas. So our initial acceleration vector is going to be 0 and negative g, so negative 9.8. And so our velocity is going to be the antiderivative of this, which is going to be 0 and negative 9.8 t plus some initial value. It's an initial value condition. So plus, we'll say like C1 and C2. Now we know that when t is 0, we should get 0 and negative 9.8 times 0 plus C1 and C2, and that's supposed to equal this vector 10, 10. Well, all that's going to imply is that C1 is 10 and C2 is 10. So here we get our velocity vector to be 10 and negative 9.8 t plus 10. And next, our position vector is going to be the antiderivative of that vector. And so that's going to give us 10t. All right, so t squared divided by 2 for the t, but then negative 9.8 divided by 2 is going to give us negative 4.9 t squared plus 10t. And then we have to consider that we may not be starting at the origin. So when t is 0, we're supposed to get, so r of 0, we're supposed to get 0.40. So that means that 10t plus c1 equals 0. I'm sorry, 10 times 0 plus c1 equals 0. So c1 is 0. That's not going to change. And we also get negative 4.9 times 0 squared plus 10 times 0 plus C2 is equal to 40. So C2 equals 40. Great. So our position equation is 10t and negative 4.9 t squared plus 10t plus 40. And so the range of the rock is going to be the distance it travels horizontally. Like we'll get to that in a moment. So the time of the flight is going to be how long this thing is in the air. So that's going to correspond to when this component equals 0. And I'm not interested in doing the quadratic formula, so let's hop over to Desmos. What was that formula? It was, let's see if I can remember, negative 4.9, and we're going to use x instead of t, so x squared plus 10x, was it plus 40? So, hold on, did I have the right formula? Yeah, plus 40. So, a few things. So one, we clearly see that we have this initial position of 0.40. We have a maximum at 1.02, and then we hit the ground at what, 4.054. So here for 3, the max height occurs at, I'm sorry, the time of flight, excuse me. So the time of flight is 4.05 seconds. Let's go to the maximum height. So we said the maximum height is going to occur when that the y component of the velocity vector is 0. So that's going to be, let's write in order. So if negative 9.8 t plus 10 equals 0, we're going to get t equals negative 10 divided by negative 9.8, which is roughly, that should be exactly that velocity, that y coordinate, the x coordinate of that parabola, but we can check anyway. So we'll say negative 10 divided by negative 9.8, and that's 1.02. So t equals 1.02. And if we substitute 1.02 back into our function, then back into this function, we would get this height of, if we look at the graph, we would get this height of 45.102. So that's how we would get the maximum height. So let's go here and say max height is equal to negative 4.9 times 1.02 squared plus 10 times 1.02 plus 40 And I think that was 45.102 things that we can see by inspection. And what else haven't we done? We did velocity, position, we did time of flight, and the range. So the range is going to be when the ball hits the ground, which should have been like the range is going to be the horizontal distance for when this hits the ground. And I think we got that at what was that value again? Zoom out. It was 4.054, and so our x component is going to be 10 times that value. So 10 times 4.054 is roughly going to equal 40.54 meters. All right, so that's our video on motion in space. We'll do this in 3 dimensions in class. It's just calculus again and initial value conditions.